I'm really glad to introduce the third speaker of the morning session. Katy is one of the main organizers here, and I'm really grateful to her for bringing us all together. And I'm even more grateful for her willingness to give this talk today. So she'll be talking about the Blob method for degenerate diffusion and applications of sampling of two-layer networks.
Okay, thank you very much for that introduction, and thank you to the organizers for this week's workshop for inviting me to speak. So what I'm going to be speaking about today, the work on a Blob method for degenerate diffusion, is going to be based on two works. The first with Jose Antonio Carrillo and Francesco Patachini, and the second with Karthik Elambezhuthi, who's a postdoc at UCLA, Matt Haberland, who's a professor at Cal Poly, and Olga Turanova, who's a professor at Michigan State. So here's my plan for today's talk. So I'm going to begin by giving a little motivation for the problem that I want to consider. And basically my goal is to design a new method for either sampling from a desired probability density on one hand, or more generally a probability measure. But also part of my motivation is to do this in a way that could also be used for designing control algorithms for robotic swarms. And in fact, my collaborator, Karthik Elambezhuthi, he comes from control theory, and during his PhD worked on exactly these kinds of fleets of robots. So it turns out that these two problems can really be put into the same mathematical framework. And my goal is to design a PDE principled algorithm for either sampling on one hand or robotic control on the other hand. So the PDE that I'm going to propose to help me solve either of these problems is a degenerate diffusion equation, a type of weighted porous medium equation. And so while on one hand it shares some properties with a maybe Fokker-Planck equation that could be a familiar PDE in sampling to this audience, in other ways it is not as well behaved. But luckily it shares one key property with the Fokker-Planck equation, which is that it has a gradient flow structure with respect to the two Wasserstein metric. So I'll talk a little bit about what I mean by that. And why it's useful in the context of this problem of designing a new algorithm for sampling or robot control. And the key reason that this Wasserstein gradient flow structure is useful for me in this context is that Wasserstein gradient flows have a really nice structure with respect to numerical particle methods. In other words, there's a really nice way that I can approximate the evolution of this PDE by a system of ODEs that describe the motion of Dirac masses in an empirical measure. And then under some assumptions, that empirical measure will converge to a solution of my PDE. So this is great. This gives me a really natural way for developing a fully discrete algorithm that could be used in practice. And so, under nice assumptions, for example, if the velocity field of your Wasserstein gradient flow is globally Lipschitz, particle methods, naturally pass between the discrete level of the system of ODEs and the continuum level of the PDE. But unfortunately, for the PDE that I'm going to be focusing on today, this degenerate diffusion equation, we lack this kind of global Lipschitz estimate on our velocity field. So to overcome that and still be able to develop a particle method for this problem, we have to introduce an appropriate regularization. And so whenever I have kind of a particle method that I combine with some regularization, that's something that I would call a Blob method for diffusive PDEs. And the reason that I use this terminology is that it dates back to classical vortex Blob methods for the Euler and Navier-Stokes equations. This is exactly what they were doing to get around the singularity of the Biot-Savart kernel. So I'll tell you what our method is, and I'll explain our main result, which is that indeed this method does converge to a solution of the PDE we have in mind that allows us to flow towards our desired distribution. And then I'll close with a few numerical examples. Okay, so let's begin by motivating the specific problems I have in mind. So throughout my talk today, I'm going to assume I have some desired target distribution, rho bar, which is a probability measure on d-dimensional Euclidean space. So if I was thinking about this problem from a sampling perspective, the question I might ask is, how can I choose samples? So I want to choose n vectors in d-dimensional Euclidean space so that, perhaps at least with high probability, they accurately represent this desired target distribution. On the other hand, if I'm thinking about this from the control theory perspective, the question I might ask is, how can we program robots to move so that they distribute their locations according to rho bar. And a key difference here is that we want this to be deterministic. So why is that the case? Well, an example of an application for this type of control theory problem is, what if you want to broadcast internet signal to a rural area using balloons? You want the balloons to distribute themselves in some way in order to maximize the internet signal. And so, what we would like is a deterministic algorithm for these balloons that still works. Maybe one balloon goes offline and then the other ones adjust their position in order to continue optimizing the signal. And we want this to be a deterministic algorithm with perhaps even some convergence guarantees, would be the goal. Okay, well, on the other hand, of course, with sampling, this is typically something that's done numerically. It's fine if you run your algorithm several times and average over the runs to get the best results. But aside from that kind of key distinction, that sampling, can accommodate some stochasticity, whereas in this control theory algorithm, perhaps we want something deterministic. They're both very similar, kind of hit this level, which is in both cases, we seek to approximate our desired target distribution by an empirical measure. So we want to construct a sum of Dirac masses, either at the locations of these samples or the locations of the robots, so that as n goes to infinity, this converges to rho bar. So in today's talk, I'm always going to be considering equally weighted Dirac masses, but if you prefer Dirac masses with different rates, our result goes through just fine with that as well. So it's well known that PDEs can inspire new ways of constructing this empirical measure. And of course, the most classical connection is between the Fokker-Planck equation and Langevin dynamics. So I think this is well known to everyone in the room, but I will recall it just because it sets up the analogy for the new PDE that I want to consider. So throughout my talk today, I'm going to start in the nicest possible case, where my target distribution rho bar is log concave. And so I'm going to say it's given by e to the negative v, where v is a convex function. And in fact, we'll often assume, or we'll often track this parameter of lambda. When lambda is positive, you can even get better results than if it's equal to 0. So, the classical approach using the Fokker-Planck equation I have up here. Here I wrote it in kind of a funny way. When I write the Fokker-Planck equation in this way, it almost looks like a nonlinear equation for rho. But if I expand out the right-hand side, I get the familiar Fokker-Planck equation, linear diffusion, with a drift term that depends on my desired target density. And one of the key properties of the Fokker-Planck equation, we consider this as an initial value problem. So we have some initial location of our density rho, and then we evolve it in time according to this equation. And why this is very not useful in sampling is that if you look at the evolution of this equation in time, and you measure how different the solution at time t is from your desired target distribution in terms of the Kullback-Leibler divergence, you can show that the Kullback-Leibler divergence actually dissipates exponentially quickly in time, kind of depending on this parameter lambda in your function v, depending on how strongly convex your function v is. So in other words, this is saying that solutions of my Fokker-Planck equation converge very quickly to my desired target distribution. And maybe this is one of the ideas that underlies the success of Langevin dynamics, is that if solutions of this PDE are flowing very quickly to the desired target distribution, then if you consider a discretization of this PDE, that should also be going very quickly to the desired target distribution. And that's exactly what you do. You take this is a nice linear diffusion equation. So you take a stochastic particle approximation of it, and you can show, in many senses that this converges to the PDE. But for example, you can even show that if you take the empirical measure at the locations of these particles, as n goes to infinity, this converges to the solution of your PDE at time t almost surely. And so then the hope is that because that if you choose t long enough, your solution of your PDE will be very close to desired target distribution, then by choosing t sufficiently large and then n sufficiently large, you can get your empirical measure as close as you want to your desired target distribution. Okay, so this is sort of the classical approach. And so in today's talk, I'm going to propose taking a similar approach, but with a different PDE. And so here's the PDE that I will propose at the bottom of the slide. You can see it actually has a lot in common with that PDE up there. It's almost as if I just got rid of the logarithm. And at first you might think that, well, logarithm is bad. It has a singularity, it's 0. So maybe by getting rid of the logarithm, the PDE gets better. But unfortunately, that's not true. I'm not going to bother expanding out the whole right-hand side because it gets a little messy. But if I expand it out in the special case that rho bar is equal to 1, I can see that this becomes a porous medium equation. So it's 1/2 times the Laplacian of rho squared. And the fact that I square rho before taking the Laplacian means that solutions of this PDE have much poorer regularity properties than solutions of a traditional linear diffusion equation. Another downside of solutions of this PDE is that we no longer, because it's not a linear diffusion equation, we no longer have this kind of rich theory of stochastic particle approximations. Okay, so those are some bad things, but there are still some good things. For example, you can even show that the Kullback-Leibler divergence dissipates exponentially quickly along solutions of this PDE. And so, would it be crazy to see if we could design a particle method for approximating solutions of this PDE, and then hope that, again, by taking n sufficiently large and t sufficiently large, we get as close as we want to a desired target distribution. So at this point, it would be very natural to object and say, well, Katy, we already have this great linear diffusion equation. Why do you want us to now study this nonlinear partial differential equation and design a new particle method for it when we already have this nice theory up top? So let me give you a few items of motivation for why I think this PDE is worth studying in this context. So the first item of motivation actually is, based on the work of several in this room. Work by Dewey et al. Identified that Stein variational gradient descent can be thought as kind of a kernelized version of this type of PDE. So in a sense, maybe understanding the dynamics of this PDE and its discretizations could in theory help shed light on some of the properties of Stein variational gradient descent. Another reason, maybe from a sampling perspective, that you might be interested in the dynamics of this equation is that just like, as some of you may already be familiar with, the Fokker-Planck equation is the gradient flow of the Kullback-Leibler divergence. It dissipates the Kullback-Leibler divergence as quickly as possible with respect to the Wasserstein geometry. This PDE dissipates the chi-squared divergence as quickly as possible with respect to the Wasserstein geometry. So perhaps if you had a motivation for wanting to flow towards your desired target distribution with respect to chi-squared, this would be the right dynamics to follow. There's also some motivation for studying this PDE and its spatial discretizations coming from numerical analysis of PDEs. So equations of this type show up in a variety of contexts across the sciences, for example, in models of porous media and biological swarming. And so, by developing a particle method for this, we have a new numerical method for simulating these types of processes. A third motivation is that it turns out the particle method I'm going to propose for this equation is a deterministic particle method, not a stochastic particle method like we had up here for the Fokker-Planck equation. And especially for these types of applications in control theory, it could be useful to have a fully deterministic method. And lastly, it turns out that the particle method I'm going to propose, we sort of realized after we wrote it down, that it turns out these dynamics correspond exactly to the dynamics of these simplified models of training neural networks. Training a neural network with a single hidden layer with a radial basis function, activation function. And so part of our analysis is going to look at what happens when you remove the regularization and send the particles to infinity. In that, from the optimization perspective, is like sending the variance of your radial basis function to 0 and looking at the over-parametrized regime where the number of your neurons goes to infinity. So we kind of identify the limiting dynamics in that case. And then you can kind of say under what conditions convexity emerges in the limit, which is, somewhat relevant for these simplified models. Okay, so now I hope you no longer think it is so crazy to study this kind of PDE. Yes? Yes. So let's talk about that a little bit at the end in terms of, I think it's a great direction for future work to understand. I'll say a little bit at the end exactly what we need about this rho bar. Indeed, I'm going to assume we know the normalization constant right now, but I think that would be a very interesting direction to see which parts of these things can be removed. In fact, yes, it turns, yeah, anyway, let's save that question a little bit for the end, if that's okay. Great. Okay, thank you. Okay, so we want to study this degenerate diffusion equation. We want to develop a particle method for it, and we're going to do that using its Wasserstein gradient flow structure. Okay, so what is a Wasserstein gradient flow? I mean, this is something that we've heard about a few times already, but let me just say it again. Basically, a Wasserstein gradient flow, this is just a probability measure evolving in time, where the time derivative of it coincides with negative the Wasserstein gradient of some energy. Or in other words, the probability measure is evolving in a way to dissipate a given notion of energy as quickly as possible with respect to this Wasserstein structure. So all of the PDEs I've mentioned today are Wasserstein gradient flows. The Kullback-Leibler divergence is the Fokker-Planck equation is the Wasserstein gradient flow of the Kullback-Leibler divergence. And this degenerate diffusion equation that I'll be focusing on today is a Wasserstein gradient flow of the chi-squared divergence. So in my talk today, I'm often just going to make a simplification, again, relating to Leon's question about the normalization constant. Because I'm always assuming that rho bar is a probability measure, I can expand this square in the chi-square divergence and write it in this way. So it's just absolute value of rho squared divided by rho bar plus constant. And this is maybe a familiar way, maybe coming from a background, I don't know, relating to problems in statistical physics. If I got rid of that rho bar, this is just a Renyi entropy. So this is, maybe a familiar way to write the problem for me. Okay, so these are two examples of Wasserstein gradient flows, or the gradient flows of these two energies. Of course, when I do the gradient flow of this energy, the constant vanishes. So saying it's the gradient flow of this whole energy is the same as saying it's the gradient flow of just that part. There are two other important examples of PDEs that have a Wasserstein gradient flow structure that will turn out to be important in this talk. One is called an aggregation equation with drift. This is a Wasserstein gradient flow of this energy. So first we have what's called an interaction energy, and second we have what's called an external potential energy. This type of equation arises a lot in models of biological swarming, and also gas dynamics, and has been kind of studied extensively over the past 15 years. So I'd say the theory here has become very mature on the Wasserstein gradient flow side. And I'd like to contrast that with a new energy that was identified concurrently in several works in the past few years, which is this energy that arises in these models of simplified neural networks, a two-layer neural network. So in this context, you have some data distribution nu, you have a target function f naught, and you have an activation function phi. So the variety of phis arise in practice, either a ReLU or a radial basis function, activation function. And then you have a parameter measure rho. And you want to somehow evolve rho to make this energy smaller. In other words, to make this parameterization closer to the target function, when viewed on your data distribution. And it was identified in many of these works that the training dynamics that people use with the mean field scaling convention is exactly like looking at the Wasserstein gradient flow of this energy. And I mentioned this here just, okay, here I made obviously a lot of choices here, like here I put the quadratic loss. So why did I make that choice? It's just because I made that choice, because when you expand the square, you can see that this energy suddenly starts to look a lot like these energies that have showed up in previous work. So if I expand the square, my first term looks like this. If I'm doing Fubini, changing the order of integration. And so this turns out to just be a kernel that depends on x and y that I'm integrating d rho x, d rho y. So very similar to this, though, of course, it depends individually on x and y as opposed to their difference, unless I pick this kind of radial basis function, activation function. And then similarly here, I end up with something that looks like an external potential integrated against rho. So I mentioned this because I think, I think this is an interesting direction, seeing to what extent the mature theory here can shed light on the dynamics of this kind of energy. And I also mention it because it turns out that in the case, if I choose phi to be a radial basis function, activation function, I can again rearrange this term so that it looks like the integral of phi convolved with rho squared d nu. And so I'd ask you just to keep this energy in the back of your head, because it turns out it's going to appear again in a few slides when I tell you how we design a particle method for this degenerate diffusion equation. Okay, so I told you a little bit about what it means that our PDE that we're interested in has a Wasserstein gradient flow structure. So how does that design a numerical method for it, a particle method for it? So a key property about Wasserstein gradient flows is that all Wasserstein gradient flows, all three of these equations, are examples of continuity equations. They can be written in this form, that the time derivative of rho plus the divergence of rho times some velocity field equals 0. So here I've put the velocity field in gold. Just to clarify my notation, it's a little odd of notation. So like, for example, here, my velocity field, okay, of course I would have to move these to the other side of the equation to write it in this way. But here my velocity field would be negative grad k convolved with rho minus grad v. Okay, so, and this velocity field, can really depend on rho. And indeed, you can even formally just see what the velocity field is by taking the first variation of your energy in the gradient and then negative sign, since we're doing gradient descent. Okay, so Wasserstein gradient flows are solutions to continuity equations. This is not very surprising since they all describe the evolution of a probability measure. So how does that help us design a numerical particle method? So here's the general recipe for designing a particle method in the nicest possible case. So let's consider that we have a continuity equation with a uniformly Lipschitz continuous velocity. So here's my continuity equation. And I'm going to put a very strong assumption on this velocity field, which is that uniformly in rho, we have a Lipschitz bound on it. Okay, so this assumption is going to be too strong, but let us have it for now because this is where the theory is nicest. Okay, so in this nice framework, how does a particle method work? Well, there's 3 key steps. So we want to simulate a solution of this PDE. So step 1 is we're going to take the initial data of the PDE, which in general could be a density of some kind, and we want to approximate it by an empirical measure. So you can do this in whatever way you like. Then what we're going to do is we're going to take the locations in this empirical measure, these xi's, and we're going to evolve them according to this system of ODEs. This maybe doesn't look like a system of ODEs the way I wrote it, but trust me, it is. Basically what I do is I take this velocity field, and instead of evaluating it at rho, where rho is the solution of this PDE, I evaluate it at this empirical measure. And basically what this does is this gives a system of n ordinary differential equations, which in general can be coupled. So the movement of the ith particle can depend on the locations of all of the other particles. It turns out that solving this system of ODEs, letting the particles move in this way, is exactly equivalent to saying that the empirical measure is a weak solution of this continuity equation in the duality with smooth compactly supported functions. And so this is one of the reasons that particle methods are so nice when studying continuity equations or Wasserstein gradient flows in particular, is that they allow you to kind of take the world of ODEs and take the world of PDEs and kind of pass between them. And so sometimes things are easier to do at the ODE level, sometimes they're easier to do at the PDE level, and they allow you to use both of those tools very seamlessly. And so if we have a velocity field that is really great, uniformly Lipschitz, we're able to show that indeed this particle method converges to a solution of the PDE. In particular, what we're able to say is that if you look at this the resulting empirical measure at time t, so you let the particles evolve up to time t, and you compare that in the two Wasserstein distance to the solution of your PDE, you can bound that above by, something that deteriorates in time times the Wasserstein distance between your empirical measure approximation of the initial data. And so at least if you're on bounded time intervals, you can see that by improving this approximation of your initial data, you're able to get that this empirical measure converges to a solution of your PDE. Okay, and so that's great. So what this tells us is that when everything is nice, particle methods converge. As long as you make your approximation of the initial data better and better, you're going to get that the solution of this particle method gets arbitrarily close to the original continuity equation. But of course, the question that is in probably the back of all of your minds is that what about when V is not uniformly Lipschitz? What about when it fails this incredibly strong assumption that I put on it? And in fact, that is exactly the case for these PTEs that I'm interested in, for both the Fokker-Planck equation and the degenerate diffusion equation. This type of assumption fails. But interestingly, it does still work for the aggregation equation with drift, as long as these this interaction kernel K and this drift potential V have bounded Hessians. And so the question arises, is there a way that we can make somehow our degenerate diffusion equation a little bit more like these aggregation and drift equations, so that we can get this same nice property that it's a velocity field, has a global Lipschitz bound. And this is where the regularization is going to come into play. Okay, so how are we going to regularize the degenerate diffusion equation to make it a bit more like these aggregation equations? And this is where we define kind of our regularized particle method, our Blob method. Okay, so at the top, I have the degenerate diffusion equation. Like we already said, this is the gradient flow of the chi-square divergence. And here's the regularization I'm going to do. I'm going to take the rho here, and I'm going to convolve it with a mollifier, phi epsilon. So you can think of this as just a Gaussian mollifier. Now, just looking at the level of the energies, one could hope that under some reasonable assumptions on rho, as epsilon goes to 0, this energy converges to the top energy. So that's the motivation for us. This is in some way approximating that energy. So if we look at the gradient flow of this energy, there's some hope, at least formally, that this gradient flow might be approximating the original gradient flow. Okay, so this gradient flow looks really weird. I got these two convolutions. It's not totally clear how this is going to help us. So now we have this really weird partial differential equation. How is that going to help us design this sort of method for sampling and control theory? But even though this is a very weird partial differential equation, it has a really nice property, which is that its velocity, which I have here in gold, is globally Lipschitz on bounded sets. Of course, that Lipschitz constant deteriorates with epsilon. So as I remove the regularization, this fails. Yes?
Yes, very interesting question. So there are two choices from this conclusion. One is to convolve function with rho, and the other is to convolve function with rho over rho bar. So in practice, or in theory, what is the right choice of what?
Oh yeah, good question. So I'm doing what I mean by here is this is the convolution. Let me add some parentheses. Oh, yes. So your question is, could you have defined the energy by saying phi epsilon convolved with rho, maybe square root of rho bar, or?
So rho over rho bar and then integrate against rho bar.
Okay. Yeah, I think, let me see if anything.
You can also get a final answer up there, but I don't know which one is better.
Yeah, let me think if I can see immediately if there was any reason that we did or did not. Yeah, I think I'd have to think about it a little bit more if there was a reason we didn't consider that one or not. But indeed, there are a lot of choices to be made here. So this is one regularization we picked, but there's other choices you could make, and another direction that's interesting to look at is other types of exponents here, like general exponents. And then when you go there, then there's maybe even more choices that can be made. But yeah, I'd have to think a little bit if what the kind of differences.
Right.
Yes.
Just one answer to this is that when you just convolve by epsilon with by epsilon, then what you really are evolving is not an empirical distribution, but a kernel density estimator, right? And so that's the only thing that actually causes the problem. With rho bar, it actually has a density already. So if you really, I mean, at least in terms of interpretation, for me as a statistician, it's much more natural to think of just involving rho itself. I'm actually involving a kernel density estimator, which actually has this really nice form that I can involve the particles and just have all along the kernel density estimator.
Yeah, I guess it would be like a weighted kernel density estimator otherwise, which somehow, yeah. So yeah. But yeah, no, I think there's clearly a lot of choices to be made. In some cases, I think we've made the right choices. In other cases, like we've also had some work on general M, and I think maybe we didn't always make the right choices there, and maybe we can make better choices now. So yeah, I think there's definitely choices to be made. Yes.
Can you just say quickly again why exactly you need the Lipschitz, the uniform Lipschitz bound?
Yeah, and from a mathematician's perspective, I may be being a little bit sloppy here. So there's a couple of problems if I try to do a particle method here. First of all, what does it even mean to define that, to evaluate that energy of the sum of Dirac masses? If I try to flow this energy with initial data that's a sum of Dirac masses instantaneously in time, it's not going to be a sum of Dirac masses because of the regularizing effect of the porous medium equation. So that's one way that you can say that a particle method doesn't make sense for this equation. It's a little sloppy of me to say it's because the velocity field's not globally Lipschitz, because this velocity field doesn't even really make sense if rho is a sum of Dirac masses. Oh, okay. Yes. Yeah. Okay, thank you. Okay, so because we have that this velocity field does satisfy a global Lipschitz estimate, even though it deteriorates as epsilon goes to 0, we at least know for all fixed epsilon that this particle method is well posed. And just turning that particle method crank that I told you on the previous slide, that standard theory, we know that at least for epsilon positive, as n goes to infinity, this is going to converge to a solution of this weird PDE that I had at the top. Okay, so of course that wasn't our goal. Our goal wasn't to come up with a particle method for this PDE. It was to come up with a particle method for the original degenerate diffusion equation. So the key question is what happens as n goes to infinity and epsilon goes to 0 at the same time. Okay, so now I have to erase this and make a quick remark back to the connection with these models from two-layer neural networks, which is that you can see this energy I'm proposing here is exactly that first term in the energy arising from two-layer neural networks. The key, rho bar plays the 1/2, plays the role of V up there, the data distribution. Now, two-layer neural networks, they have this additional term depending on an external potential V. But it turns out that all of our results are totally fine if you want to add in a fixed external potential to the energy. I just left it off for simplicity of notation. So in that sense, our identification of the continuum limit here as n goes to infinity and epsilon goes to 0 likewise sheds light on this continuum limit in these models of neural networks. Okay, so here's our main convergence result. I have it at the bottom. Basically, we do succeed in proving that it converges to a solution of this PDE. I'm going to say just a few brief words on the previous work. There actually, you may think this is the craziest particle method you've ever seen in your life, but it turns out that we weren't the first to look at this. Though all previous work had considered the case of rho bar identically equal to 1, so a uniform target distribution. So in this, this work dates back to Ohlschlager, who proved convergence of this particle method to smooth positive solutions of the porous medium equation. On one hand, this is, it's obviously the foundational work in this area. On the other hand, there was clearly still more to be done because, especially from a mathematical perspective, a lot of our interest in the porous medium equation is for those non-smooth solutions, especially for those solutions with the discontinuity in the derivative at the boundaries, things that are finitely, compactly supported. Subsequently, Leon and Moskalik, they proved kind of convergence of bounded entropy solutions. So basically what they were showing was convergence of solutions of this PDE to this PDE as long as the initial data here had bounded entropy. That doesn't really show convergence of the particle methods because clearly if you're taking the initial conditions to be an empirical measure, that doesn't have bounded entropy. But it was, again, like an important step forward. Again, we did a similar thing, again, just convergence of bounded entropy solutions. So the initial data had to have bounded entropy. But we looked for more general types of diffusion and, also adding in any sort of aggregation drift term, that's fine. That doesn't break the analysis. Only for m greater than or equal to 2. It would be wonderful to do it for m equals 1. And then most recently, in the context of these models of two-layered neural networks, John van Martin-Mondelli and Montanari proved kind of very similarly in the spirit of Ohlschlager, convergence of the particle method, again, to these sort of smooth, strictly positive solutions. And the key, a key benefit of their work is they extended Ohlschlager's argument to include these extra terms that arise in the models of two-layered neural networks, this type of external potential term. Okay, so our exact result, the key difference here is that we extend this to general data distributions, general log concave data distributions, rho bar. We're on a bounded convex domain. And whenever you have two parameters, n going to infinity and epsilon going to 0, the key question is, how are those related? How are those limits related? And so we have a sufficient condition for how those limits are related that ensures convergence of the particle method. I expect that this is not necessary. I expect that something better could be done here. So what we have to say is that the approximation of your initial data by this empirical measure, this has to go to 0 really quickly, depending on epsilon. So this is e to the negative 1 over epsilon to the d plus 2. So this is basically like saying n has to grow really fast with respect to epsilon. Like I said, I think that's probably not optimal, but because our result is not quantitative, we didn't worry about it too much. So as long as n is going to infinity really fast with respect to epsilon, we succeed in showing that our particle method converges to a solution of the continuum PDE on bounded time intervals. Okay, so this was our goal. We have developed a deterministic particle method for this degenerate diffusion equation. Just another side remark connecting this back to these models of two-layer neural networks. What this shows, the immediate consequence of our result is that in the limit of the overparameterized regime, where the number of neurons goes to infinity and the variance of the radial basis function goes to 0, the limiting dynamics are going to be convex in the Wasserstein sense, as long as the data distribution is log convex and the data distribution times the target density is concave. So it gives you conditions under which the limiting dynamic convexity emerges in the limit. Okay, so I think I actually already discussed this and intended on deleting that. Okay, so now I'll close briefly with a few numerical examples. So this just gives you a mental image of what we're doing. So here are just 3 toy examples. So in purple here, the purple lines show the target distribution we're trying to approximate. We take 100 particles. We initialize the particles. So here we have plot the particle trajectories. Obviously, we didn't plot all 100. We just plotted like 20. We initialize them just uniformly between negative 0.5 and 0.5. And then we evolve them in time. So the time axis is the vertical axis according to this method. And in order to visualize to what extent the particles are indeed approximating the target distribution, up here we plot a kernel density estimate. You can't really see the time zero, unfortunately. I think it's too faint. So the time zero is pretty uninteresting. I'll just draw it on. The time zero was just, you know, we initialize them uniformly between -0.5 and +0.5, and then we flow them forward in time. And indeed, you see that the kernel density estimate is approximating a desired target distribution. So here, this was a uniform target distribution. So this is kind of a lot of the previous work. This is a log concave target distribution. So that's where our theorem holds. And this is a target distribution that's not log concave. So our convergence result is not, fails, or we don't know yet how to do it in this case. But, you know, at least in this example, things seem to work out fine. A key principle of our approach was that we wanted to use the Wasserstein gradient flow structure to design our numerical method. One of the motivating features of choosing this PDE was that it dissipates the KL divergence exponentially quickly in time. And we indeed observe that that's preserved at the level of our numerical discretization until the discretization air saturates. But we see this sort of still exponential decay of the KL divergence. You can look at the rate at which solutions of our equation converge to the desired target distribution. In one dimension, it seems to be about first order in the number of particles. So many directions for future work. One is general rho bar, like not log concave. Interestingly, our proof for the n goes to infinity, epsilon to 0 limit doesn't really use that much about the log concavity. What's really hard is just getting well posedness of the limiting PDE when rho bar is not log concave, because you lose the convexity of the Wasserstein gradient flow structure. I think we can do it, but it's going to take a lot of work. Another key thing, relating back to Leon's original question, is what exactly is the information on rho bar that we're using here? And so a key thing is that you can evaluate this integral. Which is a pretty heavy requirement. So thinking about these are Gaussians, this is a rho bar. So this is in some sense saying you need, you know, point-wise information about rho bar everywhere in your domain. And so I think a interesting direction would be to see to what extent one might hope that instead, by approximating rho bar by something else, for example, a piecewise constant approximation of the true, you know, maybe you have some true rho bar. You sample it. You construct a piecewise constant or kernel density estimated based on that sampling. Replace that here. Run the method and then see, as you improve the approximation of your rho bar, does the method indeed kind of converge to the right thing? So I think trying to get by with less information on rho bar is clearly an important direction. Getting anything quantitative, we have no quantitative estimates. This something is, I wish someone could do something like this. I think this would be so cool. In the fluids case, they know, like these vortex Blob methods with Euler and Navier-Stokes, that by picking better radial basis functions, you can get faster orders of convergence, in particular by picking a radial basis function, so that if you convolve it with any polynomial of degree less than m, it preserves the polynomial. They can get error estimates that look like this, where m is the accuracy of your mollifier. So by picking m bigger, you can fight against that cursive dimensionality. I just think that would be so cool to get of course, we don't even have anything quantitative, so we're kind of far from this, but seems like it would be cool. And then lastly, this is truly an interacting particle system. The motion of the ith particle depends on the locations of all the other particles. So it has order n squared computational cost, quite a bit higher computational cost than, for example, Wasserstein dynamics. And so, you know, obviously in robot control context, you wouldn't want to add any sort of stochasticity, but maybe for a sampling context, you would be fine just evolving kind of some k of the particles at any time step. And it would be interesting if that still preserved the long time behavior of the method. Okay, thank you very much.
Thank you very much, Katy. Questions?
Can I ask a question?
Sure, Jonathan, go ahead.
Yeah, can you hear me well? No?
Yeah, we do.
So, I mean, so I looked a bit into like Blob version of the two-layer neural network training before, and back then, what we found is that it's a bit like just to smooth out your activation function. I mean, so instead of ReLU, you sort of do the average on activation function, and that's equivalent to the blob, I mean, to some extent. So have you guys looked into that? Or yeah.
No, I wasn't aware that there were any regimes in which the ReLU activation function could be equivalent to a radio basis function activation function.
No, it's because that you're kind of modify using a Gaussian, right, when you do the blob method.
Yeah, I wasn't, yeah, no, that I would love to learn more about that.
Yeah, sure. We can talk later.
Yeah, sounds great.
Yeah, we even have a write-up on things like that. Thanks.
Thanks.
I'd like to ask a couple of questions, if that's all right. So the first one is, like, if I remember correctly, the KL divergence contraction result that actually holds under just Poincaré. So do you expect like a Poincaré assumption plus maybe some mild extra assumptions would be enough for like the PD
Yeah,
part?
so I expect that while log concavity of the desired target distribution is sufficient for contraction of the KL, I expect that there are analogous assumptions that would be weaker. Yeah.
Okay, and the other thing is, like, could you like explain briefly like what's sort of the relationship between the blob method you end up with and SVGD, and like in particular if what you did like sheds any light on SVGD?
Yeah, that's a great question. I guess a key difference between this and my limited knowledge of SVGD is here we're really looking at the variance of the modifier going to 0. And my understanding was that in SVGD, your interaction kernel had a fixed variance.
It does have a fixed variance, but like maybe you would imagine that you would also want to eventually take the bandwidth of the kernel.
Well, then this sort of thing definitely could relate. Yeah, I guess. So something that's really nice for us is that we have this gradient flow structure. Playing with limits of these PDEs, if you have a gradient flow structure, if you have some really nice Lyapunov functionals dissipating along their flow, is a lot easier than PDEs that may lack that kind of structure. But it would still be, yeah, perhaps still something could be said.
Thank you.
Yeah, I have a very short question. How do you expect in the desired rate between n and epsilon?
Yeah, so I'll tell you what I do. So here I use the analogy. I don't know if you can see, probably you can't because it's blocking you. So like I said, these types of methods actually have a long history in mathematical fluid dynamics and numerical analysis of those equations. And they're basically the key idea is that you want to take your modifier slightly larger than the average inner particle spacing. So that's what I do here, and I get good results. So I anticipate that that kind of scaling relationship between epsilon and n, at least under some reasonable assumptions about the rho naught you're approximating, should be enough. Yes, indeed, and that's where this dimension dependence comes in the analogous fluid error estimates, because as you say, the inner particle spacing depends on the number of particles and the dimension.
We know that adding two random variables corresponds to we know that adding two random variables corresponds to convolving their densities, right? So is there any relationship between the stochastic particle method and like the convolution that you're doing in some space?
Yeah, I'm not. I'm not sure. I guess.
it's not
I'm not-
immediate, but maybe
yeah.
in some space that there might be an interpretation for this. I don't know.
Yeah, maybe. Thank you. Yeah.
All right. I also have one question. So what goes wrong, if anything, if you just try to regularize the entropy in this way, where you would convolve within the logarithm, right?
So numerically, it's okay. In terms of trying to prove the result, a key component of our proof is that, you know, we can prove some things as long as the energy you're looking at is something like this. And it's the convexity or concavity of that. So if you tried to replace this with this, it's the kind of the concavity of logarithm. Also, the singularity at 0 is bad too. So, you know, I guess from a technical perspective, it's when we try to do this Serafiti scheme, we try to get lower semi-continuity of the metric slopes. And it just, honestly, it's even harder. It's just, we can't do it. I don't know how. It would be.
So in this new paper, it's also relies on this Serafiti framework, right? Thanks.
Yeah, so that's why we don't have any quantitative rates.
Let's thank Katy again.
Yeah.
I think we resume at 2, right?